Okay, very interesting. We now know the subtle difference between the size of a pointer and the size of a block of memory it's pointing to. So let's continue in our study of pointers. Let's talk about pointer arithmetic. What happens when we increment a pointer? That is, add 1 to it. Now think about this. In the case of an integer pointer, we've learned that an integer pointer points to the beginning sequence of 4 consecutive bytes that will hold an integer. So you might think that adding 1 to that pointer variable would simply move it to the second byte of that 4-byte sequence that's pointing to an integer. You would be incorrect. Because a pointer views, in the case of an integer pointer, it views a 4-byte sequence as a single thing, as a single entity. Imagine we had an array of 10 integers. You would have 4, 4, 4, 4, or 4 times 10, you'd have 40 bytes all in a row pointing to that array. We learned that in the last slide. So initially, that pointer is pointing at the first memory location of that 40-byte string. When you add 1 to a pointer, the pointer will jump 4 memory locations to the second integer in that sequence. Add 1 more to the pointer, it'll jump 4 more to the second one or the third one. So when you increment a pointer, you jump an entity, you jump a thing. If that thing is an integer, you jump 4 bytes. If that thing is a double, you jump 8 bytes. Let's take a look at some code to make this clear. So we'll go to this URL pointed to at the top of the slide. Here it is. Now we're going to put into play some of the things that we learned earlier. So what did we learn earlier? Well, we're declaring here a pointer to a double. In this case, it's going to be a double array. We create a memory allocation, or we say, I want to reserve 5 elements of double memory. Now remember, each double takes up 8. So 5 of those is going to take up 40. By using the new operator, we tell the computer we would like to reserve 8 times 5, or 40 memory locations, by using the new operator. And we're going to store the address of where that block starts in this pointer called D5. So we declare a double pointer called D5, and it's going to point to a block of memory of 5 doubles in a row, or an array of 5 doubles. Here, we're declaring a new block of 5 integers, knowing that the integer will take up 4 bytes each. This is 20 bytes of memory. So we reserve that memory and we point to it using I5. We do the same thing with short, and we declare, so that I can illustrate some things in decimal that might be a little bit easier to understand rather than hexadecimal. I'm just going to declare a couple of useful utility variables, and you'll see how I use those in a moment. But where all the action here is we've declared a double pointer and an integer pointer and a short pointer. You need to declare what type your pointer is so that the pointer knows, if I increase it by 1, how many bytes to jump. See how that works? So now we're going to print out that the double block of memory, 8 times 5, is going to start at, and then we take the name of the pointer, which is going to be its address. That's what was returned when we reserved a new block of memory. It was the address of where that memory started was returned to that variable. And we're going to use long to take that hexadecimal and convert it to a long decimal or a very large decimal. So you won't have to do some hexadecimal math to see where it starts and how big it is. Then look at this. We're going to increment that pointer. Now, if we increment this pointer by 1, because it's a double, it's going to jump by 8 spaces. And we're going to show that by showing where in decimal, by using this long conversion, where that new location is. We're going to look at an integer. We're going to see where it starts, and then we're going to increment it, and then we're going to see where it ends up. And we're going to also do that with a short. So let's run it and see what happens. The double block starts at this large number. This large number is about 19,901,472. Now, it's a double. So we increment it, and after the increment, look at that. It's 8 bytes downstream. Because when we only added 1 to it, notice that we incremented it by the plus incrementing operator. We're only adding 1 to it. But because it's a double entity, it's going to jump by 8. Well, let's look at the integer. We're going to increment the integer here in line 16. And notice that we can confirm that it jumped 4 bytes by looking. It started at this value of 19,901,520. And when it jumped just 1 pointer increment, it jumped to 19,901,524. You really only have to look at 520, go into 524 to understand that it went just 4 bytes. Now the double went 8 bytes. The integer went 4 bytes. The short is going to go from 52 to 54. In other words, the short jumps 2 bytes every time. Isn't that fascinating? Well, I hope you're following along, and I must say that if you are following along, you're doing a great job. This can be complex, and this can be a little bit difficult to understand, but I think if you pause it and rewatch it and look at some of the code and maybe play with the code, I think you'll be able to wrap your head around it. Let's go and study a little bit more point arithmetic, really kind of circle back around and reinforce what we've already learned. In this case, we're going to see what happens when we increment a pointer variable if we've reserved already an array in memory. And you can see this in action by going to this URL. Okay, so let's check out this code. It's pretty simple here. We've just declared a pointer to a double array, and we've done so by using this new operator saying that we want a new double array of 3 elements. So the double array is going to be 8 bytes per double. There's going to be 3 doubles, so that's 24 byte sequence. And we're going to point to the beginning of it and store that pointer in this variable called P3. Now this is very interesting. We can take the pointer and we can use a subscript, just like we did with arrays, to jump to that part of this block in order to store these particular values. So if we use P3 with a 0 subscript, we're pointing to the beginning of that block. If we use P3 with a subscript of 1, we're pointing to 1 double inside of that block. If we use a 2 subscript, we're pointing to a double 2 jumps inside that block. So it's very, very similar to array notation. And in this case, we're assigning those first 8 bytes as having the value 0.2. Now that doesn't mean that there's 8 duplicates of 0.2. That means the entire span of 8 bytes codes for the number 0.2. This next thing, this P3 with a 1 subscript, says, okay, from the beginning, jump 8 bytes. And that begins an 8-byte sequence that is a double value, and that value is going to be 0.5. So 0.5 is stored in that second chunk of 8 bytes. Finally, we say 3 bytes or 3 chunks of 8 bytes down the line from the beginning. And I know what you might be thinking. I've got 2 highlighted here, yet I'm saying 3. Well, remember, this was at the beginning. This was 8 bytes down. This is now 16 bytes down. This was the first double. This was the second double. And this is, in fact, the third double. But it's 8, 16. It's 16 bytes from the beginning, and it stretches for 8 more bytes, and it's going to have the value of 0.8. I hope that's clear to you. Now, in line 12, we're going to print out that the address stored at, the value stored at P3 with no offset is, and then it's going to dump out 0.2. The value at the first 8-byte offset is going to be 0.5, and the value at the second 8-byte or 16-byte offset is going to be 0.8. Let's see if that works. It sure does. 0.2, 0.5, 0.8. But here comes something very interesting. If you look at line 15, we increment P3. In other words, P3 was where that whole block of memory started. But if we increment P3, we jump 8 bytes downstream. So you could say that P3 pointed to this at the beginning, but if we increment it 1, we now have it pointing here. Now, if P3 used to be pointing here, and we've incremented it, and now it's pointing here, the value that P3 with an offset of 0 is going to have is now going to be 0.5. And the P3 with an offset of 1 is now going to be 0.8. And that's what this is showing us. Once we increment it, that's what this space is. We've incremented it right here where the space is. After we increment the pointer, then that pointer is pointing to what originally was an offset of 1. But now the P3, because it was incremented, is pointing to that. And so the P3 with an offset of 0 is pointing to the former P3 with an offset of 1. So now P3 is pointing to this 0.5. And if we say, well, what is P3 with an offset of 1 pointing to? That would now be the 0.8. And that's what this is illustrating. Now this is certainly tricky. And so I'll go over it real briefly once again. When we reserved a new block of memory, how many bytes did we reserve? Well, each double is 8 bytes, and we had a series of 3. 8 times 3 is 24. So this is a memory allocation of 24 sequential blocks of memory, or 24 bytes. This returns the location where those 24 bytes begin, and it's stored at P3. Now, because it's a double pointer, we declared it as a double pointer, anytime we add 1 to it, it's going to jump 8. So remember, this is a continuous location of 24 bytes, the beginning of which is pointed to by P3. Because the computer knows it's a double, if it gets incremented, it's going to jump from that beginning location with an offset of 0 to 8 bytes downstream, and it's going to have an offset now of 1. Okay? But at the beginning, an offset of 0 will point to the first value. An offset of 1 will point to the second value stored there, and an offset of 2 will point to the third value stored there. And so this prints out all of those values, which you can see here. No offset, offset of 1, offset of 2. But if we increment the counter, we now move it from this position to the next position 8 bytes downstream. And so the P3 pointer is now defined as 0 offset as being what was formerly 1 offset. But then because we added 1 to it, this is now defined as the 0 offset. This would be 1 offset downstream. There is nothing 2 offsets downstream. That would go beyond the bounds of what we've allocated. And that's very dangerous to do. And as a programmer, you have to pay attention to where the bounds are. The software will not stop you from leaving the boundaries, and you can create all sorts of problems. But to illustrate that after we increment it, we've now redefined the starting point, which used to be here, now it's here, which means the offset of 1 would be 0.8, and that's what this confirms. Very complex. Take a look at this. Go ahead and think about it and ask me questions if you have a hard time.